Hello students, welcome to this next session on the subject of industrial metallurgy. We are covering the chapter of alloy systems. In this session 13, these are the contents that will be covered. Particularly, we'll talk about transitional phases, or what are also called intermediate phases, in this session. Okay. So now we would be discussing about intermediate phases, which are popularly also called transitional phases. And first we'll see what exactly is meant by an intermediate phase, under what conditions does it get formed, how is it different from a solid solution, and then we'll discuss about its three categories or three types. Now, to understand or to explain what is meant by an intermediate phase or a transitional phase, let us assume that you are trying to form an alloy with the help of two elements, M and N, where M is the solvent and N is the solute. Now, importantly, assume that the amount of solute that has been taken is more than what is the solid solubility of the solute in the solvent under room temperature conditions. I repeat, we are trying to form a binary alloy with M element as the solvent taken in more quantity and N element as the solute, but the amount of solute that has been taken is more than the solid solubility of this solute in the solvent under room temperature conditions. For example, let's assume that under room temperature conditions, the solid solubility of that in the solid state, the amount of solute that can actually go into solvent is 15%. But to form the alloy, we have taken, say, 21% of solute and remaining solvent. So we have taken solute in an amount which is more than the solid solubility of the solute in the solvent. Now, if that is the case, because these are two elements are capable of forming a solid solution, the first phase that will get formed would be a solid solution of N in M. N in M means a solid solution will get formed with N as the solute and M as the solvent. But now, because N has been taken in an amount, in a weight proportion, which is more than the solid solubility of N in M, that means the solid solution N in M which has got formed will not be able to accommodate the whole of N that is there in the alloy. So this excess of N will get precipitated out and would also pull along some M along with it. And so a second phase will get formed. And this second phase, in a very, very few cases, would again be a solid solution, with the difference that now N would be the solvent, it would be in more amount, and M would be the solute. So you will have two solid solutions, a solid solution where M is the solvent and another solid solution which has precipitated out in which N is the solvent. But as I said, this second phase that is precipitating out only in very, very rare cases would be a solid solution. In most of the cases, this excess of N and some M being drawn out of by it, these two would not form a solid solution again, but rather would form a chemical compound. So if in a metallic system, a chemical compound gets formed because the solid solution precipitated the excess of solute out of it, this chemical compound, which would be very different from the conventional chemical compounds that we talk about, this chemical compound formed in metallic systems is called intermediate phase, or is also called transitional phase. Okay, now these intermediate phases or interstitial phases, as the flow diagram was showing, are of three main types. Let's discuss the first type, which is called interstitial compounds or size factor compounds. Now students, this type of an intermediate phase will get formed if you were trying to form an interstitial solid solution, and in that interstitial solid solution, the amount of solute that had been taken was more than the solid solubility of the solute in the solvent, and then the excess things which have precipitated out have formed a chemical compound. They might be an intermediate phase, but for them to be an intermediate phase, the other things that I'll list down over here must be met. Now, interstitial compound or size factor compound is only formed when solvent was one of these metals, either scandium, titanium, tungsten, or iron. And these are the solvents, and we had taken as solute a very small sized atom which might have been boron or carbon or nitrogen. And when this compound gets formed, it's not only that if these two things, this as the solvent and any of this as the solute is present and an intermediate phase is getting formed, that intermediate phase would always be interstitial compound or size factor compound. No, the other things must also be met, which we are discussing now. So the crystal structure you see of the solid solution is always that of the solvent, but the crystal structure of this intermediate phases is always different from that of the solvent. The crystal structure is different from their parent interstitial solid solutions, right? And if it is an interstitial compound, this crystal structure depends upon a ratio Rx by Rm, where Rx is the radius of the solute atom and Rm is the radius of the solvent atom. And we have to see what is the value of this ratio. It has been observed that if this ratio is less than 0.95 or equal to 0.95, as I have listed in the last sub bullet point, if this Rx by Rm ratio is less than or equal to 0.95, the crystal structure must be simple. It can be body centered cubic, FCC, or HCP. And in case this Rx by Rm ratio is more than 0.95, then the crystal structure must be complex. Why I'm saying this? Because if this condition of satisfying the Rx by Rm rule is not met, then this intermediate phase that is getting formed may be something else. If it is a size factor compound or an interstitial compound, it has to meet this, it has to show the crystal structure according to this rule. Okay. I have given you an example also over here, that cementite or iron carbide that is formed in all steels and cast irons, the Rx by Rh ratio is 0.63. Now, since this ratio is more than 0.59, the crystal structure must have been complex for cementite to be an interstitial compound. And exactly that happens. Cementite has got a very complex crystal structure which is basically orthorhombic, having 4 carbon atoms and 12 iron atoms per unit cell. Then what are the properties which are shown by these interstitial compounds or size factor compounds? You see, they are true alloys and have highly metallic properties. They have got highly melting points. The main characteristic of interstitial compounds is that they have got very high value of hardness. So all cutting tool tips, titanium nitride, titanium tungsten carbide, which are used as tool tips because they have to do cutting at very high speeds, so they must possess very high hardness. All those compounds are nothing but interstitial compounds. And another thing is that these intermediate phases, these compounds behave as conventional compounds in the sense that they always get formed at a fixed ratio of their constituent elements. So Fe3C, Fe4N, TiC, TiN, etc. are examples. Now let us move to the next type of intermediate phases. They are called Hume-Rothery compounds or electron compounds. Students, these are intermediate phases which are always formed at a definite value of electron ratio. What is this electron ratio? Electron ratio is defined as the ratio of the number of valence electrons present in the compound to the number of atoms present in the compound. And for an intermediate phase to be a Hume-Rothery compound, it has been investigated and found out by researchers that this electron ratio that we are defining will have 3 specific values only. Either it would be 3/2 or 7/4 or 21/13. So these 3 ratios are 21/13, 21/12, and 21/14. So that cuts down to 3/2, 7/4, 21/13. And if this compound is getting formed and it has got one of these ratios, and we'll explain with an example how do we arrive at this 3/2 or at 7/4 or at 21/13 means what exactly does it mean. I'll show it to you on the next slide. But then if a chemical compound in a metallic system has got formed with these ratios, the crystal structure of the intermediate phase, the compound that has got formed, depends upon this ratio. If the ratio is 3/2, the crystal structure must be BCC. It can be HCP or complex, but there is no fourth option. If the electron ratio of the chemical compound was 7/4, if it is a HuMRO3 compound, it must show an HCP crystal structure. And if the electron ratio for a intermediate phase comes out to be 21/13, and if it is a HuMRO3 or an electron compound, it must have a complex crystal structure. Okay, so here I am taking two examples to explain as to how do we calculate this electron ratio. AgZn, valency 1, valency 2, number of atoms 1, number of atoms 1. So what are the total number of atoms? 1 of silver and 1 of zinc. What are the total number of valence electrons? 1 for silver, 2 for zinc. So what is the total number of valence electrons to the total number of atoms? It's 3/2. So the electron ratio comes out to be 3/2. Similarly, we take another popular example, Cu9Al4. What are the total number of atoms? 9 of copper, 4 of aluminium. So what are the total number of atoms? 13. And 9 into 1, 4 into 3. These are the number of valence electrons. So what's the electron ratio? Electron ratio comes out to be 21/13. What are the characteristics of these intermediate phases, which we call as HuMRO3 compounds or electron compounds? You see, they have got exceptional high value of ductility. Their hardness is always very low. And one thing which makes them very different from the conventional chemical compounds is that they are not bound to obey the rules of chemical valence. Means there is no binding on them to complete their octet, to complete their valence shell. They are only interested in achieving this electron ratio, either of 3/2 or of 7/4 or of 21/13. Okay, so what would happen, even with the same constituent elements, they can get formed in different ways with different chemical formulas to satisfy just this condition of electron ratio. We come to the final type of intermediate phase, the third type, intermetallic compounds or valency compounds. See, as the name only suggests, they will always get formed when you were trying to form a solid solution taking two metals. So they are always, these are chemical compounds which are always formed between metals. But the interesting thing is that both these metals are chemically very dissimilar. Because they are chemically very dissimilar, when these excess of solute comes out, taking along some of the solvent with it, these two metals that are now coming out will preferably join with each other, bond with each other through a electron compound or through a covalent compound. And because they join through an ionic compound or a covalent compound, this intermediate phase essentially will have non-metallic properties. Right? Okay, crystal structure would always be very, very complex. You cannot have an intermetallic compound or a valency compound which is showing you some simple crystal structure like simple cubic or BCC or HCP or FCC, etc., etc. It would always be very, very intricate type of a crystal structure. So what are the properties? See, the first two type of intermediate phases, the interstitial compounds and the electron compounds, they were essentially metallic, but this third category is essentially non-metallic. And because of the strong electrovalent and covalent bonds, these compounds, these intermediate phases that are getting formed will have exceptionally high melting points. They will have very poor ductility as well as electrical conductivity. And some of the examples are CaSe, Cu2Se, Mg2Sn, Mg2Pb, etc. So students, I think this is now clear as to what are the two main types of phases based on the properties. They are solid solutions and intermediate phases. We have discussed the two types of solid solutions, and now we have discussed the three types of intermediate phases that can get formed in alloy systems. Thank you for watching. Thank you so much.